Hi everyone, and welcome back to another AP Calculus video. Today we're going to introduce you to the concept of parametric equations. And in order to do that, I want to remind you of a fun toy that maybe you played with as a child called an Etch-a-Sketch. And what an Etch-a-Sketch does is it allows us to create a picture by simply turning two knobs. And I want you to think of these two knobs as being our x-coordinate and our y-coordinate on our graph. Now, if I take the knob that's on the right side and I turn it one way or another, it'll create a little line, a horizontal line. So one of the knobs will make the little magnetic piece behind the screen go left and right. Now, if I do the other knob and turn that, it'll go up and down. And what you see here is that you have one knob that defines the left-right motion and one knob that defines the up and down motion. And if I make them work together and turn them, maybe at a different speed, maybe there's a different function that drives it, as I crank, I can create little, designs here. And some people get really, really good at drawing these Etch-a-Sketch. I am not, especially not on a computer where I have to use the arrow buttons. But this website here is kind of a fun little website that allows us to see how an Etch-a-Sketch works. And what I want you to understand is that as we begin to discuss this concept of parametric equations, and here we'll clear out our Etch-a-Sketch, as we talk about these parametric equations, I want you to think of them as individual equations for the left-right motion of a particle and the up-down motion of a particle. And that can be kind of considered a specific type of parametric equation in the family of equations that we like to call vectors, which is part of what we talk about when we discuss parametric equations. But essentially, I want you to think of it like this. If we're going to graph it on a two-dimensional piece of paper in two variables, parametric equations are separate equations that will define the x-coordinate, and then you have a different equation that defines the y-coordinate. And so as they move together, depending on the rate of change, which we call the derivative, depending on how these functions behave for the x-coordinate and the y-coordinate, when they move together, they plot a particle in space, not simply moving left and right, but moving left, right, up, and down, and together, and it creates curves, and it creates fabulous two-dimensional designs that are pretty cool. So let's take a look at what parametric equations actually look like. Now, one very basic type of parametric equation that we can take a look at is the unit circle from pre-calculus or from trigonometry. Now, we should know that the unit circle is simply a circle that has the equation x squared plus y squared equals 1. It's a circle with a radius of 1. And as we travel about on that circle, the x and the y coordinate give us the cosine and the sine of the angle created with the x-axis respectively. So we're familiar with angles like pi over 3, pi over 6, pi over 2, pi over 4, or at least we should be. But it's really important to understand that anywhere along this circle, you're going to be able to find the sine or the cosine of the angle, even if it's not one of those nice unit circle values that we're made to memorize. And so we can actually graph this as a parametric equation. And in Desmos, the way that we graph parametric equations is as an ordered pair of equations. So you can see here below the equation x squared plus y squared equals 1, you see this set of coordinates where the x equation is the cosine of this variable t, which we're used to calling it theta, but we're going to start calling it t. T is what we're going to call our parameter. The y coordinate is the sine of t, which is the angle, that's our parameter. And if we graph the set of points between 0 and 2 pi, that's 1 revolution, check it out, I'll turn this on. It creates the blue circle that overlaps with the red circles. They're the same graph expressed two different ways. And the red graph, the red equation, x squared plus y squared, we refer to that as a Cartesian equation or as a rectangular equation because it is using x and y, the variables, and rectangular meaning to go from one point to another, we would travel rectangularly over x and up y, creating a rectangular kind of pattern of plotting those points. Cartesian because the x and the y grid system was developed by René Descartes. And so, of course, if you develop it, you get to have it named after you. The parametric way of graphing this simply says, here's my x-coordinate. It's defined by the cosine of t. Here's my y-coordinate. And so this is a picture of all the x and the y-coordinates defined by cosine and sine of the angle made with the x-axis. Now, the cool thing about parametrics is that I can actually change what we see. So instead of going 0 to 2 pi, if I only wanted to see half the circle, I could just change my parameter, and now I'll go ahead and turn off the red circle. Here's my half of a circle from 0 to pi. If I wanted to see the bottom half, I'd simply go from pi to 2 pi, and that gives me the bottom half of the circle. If I simply wanted one quadrant, I could go from 0 to pi over 2, and this gives me a quarter of a circle. If I just wanted to see 1 radian, I would let t go from 0 to 1. And this is what 1 radian is. And by the way, the definition of a radian is it's the angle created when you take the radius of the circle and measure that linear distance. So the distance of this curve, if I straightened and flattened it out, that distance would be 1. That's the definition of a radian. So a radian is that angle created by that arc length. Where the arc length, that's the word. Arc length is the radius of the circle. So this is an arc length of 1. Therefore, the angle the wedge created is 1 radian. And there's about 6.28 radians in a circle. I'll let you think about that number. But basically, this is how a parametric equation works. We can look at snippets of a graph and see how it behaves. And the cool part is that as we look at these parametric equations, if t is defined as being, from point A to point B, we have endpoints on our graph. And we're going to be learning very soon here that we're going to refer to those endpoints as the initial point. That's where it starts. So when t is 0, that's my starting point. We call it my initial point. And my terminal point is that last value of t. So here the terminal point would be when t is 1. And we could find the x and the y coordinate by simply plugging in 1 for t. So when you get into your calculator, the cosine of 1 in radian mode would be the x coordinate up here when t is 1. So we can find the x and the y coordinate by using t. T is kind of a hidden variable. We refer to it as the driver. It's not ever graphed. It's just kind of in the background, controlling what happens with x and y. Now let's take a look at a new set of parametric equations and a different way that they might be expressed. You saw in Desmos that when we graph parametric equations, we simply graph them as an ordered pair of equations. Typically when we write the equations, we say x equals or y equals. We can use the expression x of t or y of t. That also works. But basically we're defining this function, and I want you to understand y equals f of x is that rectangular or Cartesian expression of the function involving both x and y. But we define it as two equations, one for the x coordinate and one for the y coordinate. And it's always in terms of this parameter. We generally call it t, but you can use whatever letter you want. Theta would be another example of a parameter that we might see. So here are two equations. We've got x defined as the square root of t and y defined as t minus 2. So let's take a look and see what kind of graph these parametric equations create. So here they are, my x coordinate and my y coordinate, and I've defined t as being between 0 and 1. If I redefine it as 5, I get more of the curve. If I let it go all the way to 100, I see that I get a lot more curve. I'm going to have some trouble here trying to define t as being anything negative just because of the x value being defined as the square root. It's not in the domain. So basically I get half of this graph, excuse me, and it goes on forever, and whatever t is, that's going to kind of define what happens with my function. And if I zoom way out, and when t is 50, it stops way up here. So you can see we kind of have a lot of control over how much of that graph that we see. Now, as we're looking at this graph, we can kind of see, the shape and everything. But we want to also talk about how we could graph this. What would be the equation if we were going to graph it as a function of x? What would it look like? Well, if we take the two equations, x equals the square root of t and y equals t minus 2. If I wanted to write it as an equation, my goal is to write it as y equals, and then instead of t, I want to replace the t with x's. So what makes sense to me is to take the x equation and solve it for t. So I want to solve the x equation for t equals, well, t here equals x squared. Once I know what t is, then I simply take what I found and replace the t with the x squared. So I end up getting this equation, y equals x squared minus 2. Now, if I take this equation, this new rectangular Cartesian equation, and go back to my Desmos space and graph this guy, what's going to happen is it's going to show the entire graph, y equals x squared minus 2. And let me change the color here so it doesn't show up as red. But basically, here's what happens. My parametric equation is still there, and you can kind of see it underneath. Nope, that's a 2, not a 3. There we go. You can see that parametric equation, and it's the same. The difference is by defining the parameter t, and by knowing that t can't go less than 0 because of that square root of t business, the parametric equation only shows part of the graph. So the rectangular graph will graph the entire thing in its the entire graph. I'm sure that there are problems here with the domain and the original domain restrictions. Probably we'd have to list something saying, oh, well, you know, x can't be less than 0 because of the original parametric equation. But that's not something that we're going to get into necessarily here in this video. We're just getting our feet wet and exploring what these parametric equations are all about. So if the parameter is defined on an interval, then we have these endpoints, right? So let's talk a little bit about what our endpoints, what our initial point and terminal point will be. So if we stick with that parameter where we said t is going to be between 0 and 5. So let's go ahead and give it a definition. Nice and easy. Well, the initial point, to find the x and the y coordinate, I would simply go x of 0 equals the square root of 0. So the x coordinate is 0. The y coordinate is 0 minus 2 or negative 2. So 0, negative 2 is my initial point. My terminal point comes from this last part here. So I do x of 5, so that would be the square root of 5, and then I do y of 5, that would be 5 minus 2 or 3. So I'd have this square root of 5 comma 3 would be my terminal point. That would be the ending point for this particular graph. Now that may change if I change my parameter and redefine it, but essentially this is how a parametric equation works. So now that we've had a chance to look at parametric equations, and this is meant to be a good introduction to how they work and what they're about, the next video is going to dive a little bit more into the calculus involved with parametric equations. In the next video, we're going to talk a little bit about how to find the derivative, how to apply the derivative, and even how to find the second derivative and apply that to finding points of inflection on our graph. So, I hope this has been a good, helpful video for you, and stay tuned, keep watching, and keep at it. You've got this.